I'm going to help you with your homework. You always like it when I do. If I have a block sitting on a level surface, is the normal force equal to the weight in magnitude? Yes or no?
Yes.
Yes, it is. What if I put that same block on an incline? Now it's no. Okay, and I can show that with a free body diagram. The first force I put on any diagram is a weight. Then ask, are there any magnets? No. What touches the block? The ramp, the incline. Does a push or does a pull? It pushes. Whenever one thing pushes on another, I will always have a normal force. I may also have a friction force. If this is dry ice on slate, there would be no friction and it would speed up down the ramp. If I were to tell you that it's moving down the ramp at a constant velocity, that would tell you there has to be a friction force. Now folks, ramp problems are hard. Ramp problems are messy mathematically. Ramp problems require you to solve two equations and two unknowns. Unless you look at them just right. And I'm going to show you how to look at them. Okay? You got to tip your head so that it lines up with the ramp. In other words, you have to rotate your coordinate system. If you rotate your coordinate system, all the forces in your free body diagram will line up with your coordinate system except one. But it's always the same one. It's always the weight force. And you always break up that weight force into components the same way. Now people, I'm an old man, I've been doing this a long time. On the midterm, you're going to do it a whole lot of ways, a whole lot of different ways. But there's only one way that I'm going to call the right way. Okay? The right way is you look in the direction of the normal force and you go the other way until you can make a 90-degree turn. There's my 90 degrees, and get to the end of that weight vector. If you break it up that way, then this angle here will be that angle there. Okay? If you break up your weight vector that way, those angles will be the same. Now, once you've broken up a vector into its components, you throw away the original and use the components. Once I've drawn a free body diagram, I get to use Newton's second law twice, once in what I'm calling the y direction and once in what I'm calling the x direction. If there's no acceleration, this diagram has to scream balance in both directions. That means the normal force is equal to the y part of the weight. The friction force is going to balance the x part of the weight. Well, if the normal force balances just the y part of the weight, just part of the weight must be bigger than the normal force. And folks, that's the point, pardon the pun, behind the steep roofs on chalets in Montana, in the mountains. You want that roof to be as steep as possible, because the steeper that roof, the smaller the normal force for a given weight of snow. And the friction between the roof and the snow depends on that normal force. You want that friction to be small so that the snow will slip off, will slide off, and not crush your house. Okay? Now, I was hurrying because I wanted to get to this sample problem. This sample problem is very, very similar, by which I mean almost the same, as two of your homework problems. And you will definitely have a problem like this on the midterm. You have a 70-kilogram skier skiing down a slope that's angled 37 degrees. On your exam, it'll be 53 degrees. Okay? The coefficient of kinetic friction between the skis and the snow is 0.1. What is the skier's acceleration? Well, that's what we know. The mass and the coefficient of kinetic friction. We know the acceleration is down the ramp, but we don't know how big it is. We've known it's down the ramp since the first tutorial. We start with a free body diagram. We put the weight first, then we ask, are there any magnets? No, Greg, you're being silly. What touches the skier? Well, the hill, and it pushes. The snow pushes with a normal force on the skier, and it pushes with a friction force. We know there's a friction force because we're told what the coefficient of kinetic friction is. Now, this problem will be very, very difficult, requiring 2 equations and 2 unknowns, unless you tip your head. If you rotate your coordinate system to line up with the hill, then all the forces will be lined up with your coordinate system except for this one. We break up that weight force by looking in the direction of the normal force. Are you listening to me, all of you? Look in the direction of the normal force and go the other way, till you can make a 90-degree turn and get to the end of that weight force. Okay? And that gives me my components. Now, which angle is 37 degrees? I'll show you a way to remember that forever. I have a spike through a board and a plumb bob. And when I have the board horizontal, the plumb bob and the spike are in the same direction, down. As I move the board up, it pulls the spike away from vertical. The more I pull the board up, the more the spike goes away from vertical. Let me show it on the screen. There's a spike, there's the plumb bob. The plumb bob always points straight down. As I move up the plank, the spike is moved away from vertical. The more I move it, the more the spike is moved away from vertical. So that those 2 angles have to be the same. Now, the plumb bob represents the weight force, always pointing straight down. The spike represents the negative y direction, which is the y component of the weight. So if I go back here, there's the spike, there's the plumb bob. So the angle that's going to be the same as the board is this angle between the spike and the plumb bob. That make sense? Now, we're almost done. We got 1 minute. It's the most important minute of your life, I promise. You'll never have a more important minute. Once I break that force, the weight force, into its components, this is going to be 700 times the cosine of 37, 700 times the sine of 37. I can use Newton's second law in both directions. In the y direction, there's no acceleration. This has to screen balance in the y direction. If I've got 560 in the minus y direction, I have to have 560 in the positive y direction. Once I know the normal force, I can find the friction force because I have this coefficient. I just take the normal force and the coefficient and I multiply them together. That's the friction. If I take a tenth and multiply it by 560, I get 56. Now, last step, I use Newton's second law in the x direction. I have 420 newtons down the ramp, so it's positive. I have 56 newtons up the ramp, so it's negative. That equals the mass, 70 kilograms, times the acceleration. That gives me an acceleration of 5.2. Notice that this is less than 9.8. That is the goal of skiing, to keep your acceleration less than 9.8. If you get to 9.8, your mom's not happy. Okay, we're out of time.